Hi, this is Evan, and today we'll be going over how to calculate the change in height with a three gravity drain tank system. Okay, so today our prompt reads three gravity drain tanks, each with a constant cross-section area of 1 meter squared and a whole area of 0.05 square meters. Are connected such that the inlet flow to the first tank drains sequentially into the second, the third, and out of the system. The system is initially at steady state with an inlet flow of 1 cubic meter per second and is protruded by a reduction in the inlet flow to 0.5 cubic meters per second. So our goal here today is to derive a differential equation describing the liquid levels in the three tanks and simulate the response in a liquid height of three tanks arising from the decreasing inlet flow. So first, we will describe this equation on the whiteboard, working through the problem and to get the derived equation. And then after we fully derive the equation, how to solve this, we will put this equation into Python so we get a mathematical value. So let's walk through this, the figure. So here I already have three drawn tanks draining down. So we know that we have a inlet flow, so we call this Q1 and Qn. Inlet flow flowing to our first tank. Okay. We know that the tank, whoever goes to the tank flows out of the tank. So we call this Q2, then Q1, and then flows into the next tank. Okay. So it'll be the same thing for the next one. Q2 flows out of tank 2 and flows into tank 3. And then from tank 3, you have a leaving flow of Q3. All right. Let's start with A. Let me put this to more of Q. Q1. Okay. We also know that the system was in a steady state. So we can also assume that the heights of all tanks are equal. They start off equal at least. Okay. So you assume all of these ages, all these heights, height level of the liquid, all equal. You can also assume the cross-sectional area of all these tanks, so this right here, AC, is equal throughout all three tanks. Okay. So we know our height of the tanks, we know the cross-sectional area of these tanks, we know also the cross-sectional area of the holes for each tank, which are also equal. And what we need to find is the change in the height. So we need to essentially find the change that we see in respect to time. Okay. So that's our main thing we're trying to find. Okay. So how do we do this? Okay. Well, first let's think this general. So right now we have a volume of liquid in a tank. We know what's going in and what's going out will change what's initially in the volume. So we have the change of volume, dV, divided with respect to time, is equal to Qn minus Q out. Okay. So we know that the change of volume is due to the whatever flows in minus whatever flowing out. Okay. Now we also know that volume is equal to area times height. Okay. So instead of saying dV, the difference in volume, this can equal out to the difference in height, respect of time, times area, which here the area is cross-sectional area of the tanks. So it'll be times AC. So our equation for the differential height for all three tanks would be dH divided by dt times cross-sectional area AC is equal to flow in, Qn, minus flow out. Okay. So let's write it down for all three tanks so we know what's going on. So for tank 1, this would be dH1 dt is equal to Qn, AC, sorry. It's equal to Qn minus flow 1 liter. So liquid going in tank minus liquid going out. Next tank. Cross-sectional area. Let me move it out a bit more. Cross-sectional area of the tank times the difference in height in tank 2 divided by expected time is equal to the flow of tank 1. So Q1 minus the leaving flow of tank 2, Q2. All right, and then in tank 3, same thing as tank 1, tank 2. Cross-sectional area times differential height in tank 3 divided by change in time is equal to flow of the leaving liquid in tank 2 minus flow out of tank 3. So this is our equations, differential equations for all the tanks. Okay, so now we should be good, right? No. So right now we know what's going in. Oh, we do not know the flows of Q1, Q2, or Q3. Okay. So next we need to find how do we calculate Q out. Okay. Now, well, equation, other formula we could use that can help us in this situation is Bernoulli's equation. So Bernoulli's equation states is a relationship between, well, first Bernoulli's equation is a relationship between pressure and velocity in a system. Okay. So it states that the pressure is right. The final pressure minus the initial pressure divided by density plus the gravity. Let me see it. Gravity times the potential energy, difference in potential energy. So Z1, Z2 minus Z1 plus the difference in velocity. So V2, you see, V2 minus V1 squared divided by 2 is equal to 0. Okay. So the change in pressure divided by density plus the gravity times the potential energy of the system plus the change in velocity in the system squared divided by 2 is equal to 0. Okay. So we use this to solve for Q out. All right. So first we know, let's start with difference in pressure divided by density. Well, one, we know here that the holes, the two big holes, we have our inlet hole and it's our hole leaving the system. Both are in contact with the atmospheric pressure, ATM. Okay, they're both in contact. So the pressures of both of these two areas are equal to each other. So P2 and P1 cancel out to 0 because they're equal to each other. So this cancels out. All right, so first part gone. Next, we have the gravity times the potential energy of the system. Okay. So potential energy right now is described here as height. So right now, we start out initial height, a random height, we don't know that right now. We have initial height here. We know that the height over time will trickle down to some height we are not unknown yet to H5. Okay. The potential energy, for potential energy, the more you decrease your height, initial height from your final height, the less the smaller the potential energy is. So you have a negative term for your potential energy. So this right here, respect to height, would be negative GH. Okay. Because we want our height to be positive, right? We want our height to be positive. So we know that the potential energy is decreasing. So it has to be a negative for the potential energy. And lastly, we have our velocity. All right. Now, we have 2 points in our tanks. I'm just keep using this because that's most. We have point 1, where flow is going in, and point 2, where flow is leaving. Okay. Now, right now, we're making it in terms that QN is currently being changed from 1 meters cubed per second to now equaling 0.75 meters cubed per second. Okay. Now, when this change occurs, we know that this won't be affected by this change instantly. The inlet velocity and the outlet velocity will still be different. For this term, the outlet velocity in tank 1 will still be greater than the inlet velocity in tank 1 because it takes time. That's why we have the height respect to t to see that those changes in the velocity, in the velocity in tank 1 leaving. So at this time, when Q and the velocity, the liquid velocity going into the tank is changed to is reduced, the velocity leaving the tank is currently higher. So Q1 is greater than the inlet velocity. That's G. Is greater than the inlet velocity. Okay. And it's so much greater because 1, the flows change. Even if the flows didn't change and it remained 1, the cross-sectional area of the hole makes it so that the flow going out is way greater than the trickling effect of the volume going down inside the sink. Okay. So, because we know that the sink will move slowly and slowly down over a vast period of time. While here, the liquid going outside this tank is moving extremely fast due to the small cross-sectional area of the hole. Okay. So when we square root this term, we square root velocity of 0.2 velocity of 0.1. The size of velocity of V1 will be so small compared to V2 that would be basically irrelevant for this equation. It wouldn't affect the change of V2 at all when we square root both sides. So we can take V1 away and we'll be left with velocity of stream 2 divided by 2 squared. Well, velocity, the stream of velocity, the second point velocity squared divided by 2. Okay. And we set all this equal to 0. Okay. So now our new equation is stream 2's velocity squared divided by 2 minus gravity times height is equal to 0. All right. Now, what are we still trying to find? That was a lot. All right. We are still trying to find Q out. So we need the velocity. We need to find how much, what speed is the liquid leaving from the tank. All right. So we need to find V2. All right. So let's get V2 by itself. So we do algebra. Move this GH both sides, multiply both sides by 2. And we square root it as well. All right, we did all the steps at once. We will get that velocity at 0.2 is equal to gravity. Well, is equal to square root of 2 times the gravity times height. Okay. So this is the velocity leaving, is the equation for the velocity leaving each tank. So it works for this tank, and this tank. This is the equation to find the velocity flowing out for all the tanks. Okay. Now we already know for Q out that you need the cross-sectional area times velocity to get the actual flow going inside the volume. That's how we got Q in. Okay. So Q out would be equal to the cross-sectional area of the hole times square root of 2GH. All right. So that's our Q out. So now we know our Q out. So now our equation will look like the change in height divided by the change in time times the cross-sectional area of 0.1 will be equals to the flow rate going in minus cross-sectional area of the hole leaving the system times square root of 2 times gravity times the height. Okay. So now that is our new equation for the change in height. All right. So we now know our change in height with respect to time. We know our Q out. So are we done? We are not. Okay. We need one more thing to finish this off. Is that we do not know, like I stated before, if you did catch it, we do not know the initial height of any of these things. We do know that the initial height, let me put this initial, is all equal to each other. But we don't know what the things are. We don't know what initial height starts at. And that's very important. Because we can have an equation stating that, oh, we know exactly the rate where the height is decreasing. We don't know what exact height you're decreasing from. So let's find the initial height for all these things. So for this, we're going to use the new equation that we just found. Okay. But in this case, we'll set the change in height as 0 because we're making this so that the initial height. So there will be no change yet. So this, the dH over dt will be set to 0. All right. So the new height, I'll do it over here so you can see. The new height, to define the height, we'll have 0 will be equal to, oh, before I do this, actually, I want to make a mistake. I forgot to do this earlier as well. But for Q1 over Q out, I need to change this. The cross-sectional area needs to be flipped over. So we can do it here. So the AC needs to be, the DH over DT needs to be by itself. Okay, so this is a mistake I did make. So AC over DH over DT is equal to QN minus Q out. You want DH over DT by itself. So you need to divide both sides by 1 over AC. And the new formula should be DH over DT is equal to 1 over AC times QN minus Q out. Okay, this is what it should look like. So these are all incorrect. Well, they're correct, but they need to be respected. AC divided by cross-sectional. Okay, so now that all of our equations are now correct, let me also change this side. I'm still on board. Okay, so now that's set. Our equation will be 0 is equal to 1 over cross-sectional area times QN minus the cross-sectional area of the whole square root of 2GH. Okay. So now we need to find the height right here. Let's do more algebra. We can get easily solve this. So you want to move AC to this side to go equal to 0 because 0 times plus anything will be 0. So now you have 0 is equal to QN minus area of the whole square root of GH. Move this whole section to this side. You have cross-sectional area, cross-sectional height, area root of 2GH equal to QN. Okay. And then do more algebra, divide AG, AH to this side, square root both sides, then divide both sides of this, the G, and 2 and the G. And this will be, drum roll please, H is equal to 1 over G8, 1 over 2G times flow in divided by area of whole squared. Okay, so this is our initial height. Okay. This is our initial height. All right. So we have now found, let me see. Change this as well. So we have found the difference in height, respect to T equation. We have found the equation for the flow going out of each tanks, which is right here. And now we have found the initial height that each tank will start at. All right. So now with all this information, we have enough to now officially start our math for and plug this all into Python. So I will see you guys in the next part.
Hi guys, I'm back with part two of the three drain tank system. The first part we did earlier on the whiteboard where we wrote down our problem statement. We wrote down the differential equations for all the steps to figure out the change volume for the three drain tank system, and now we're going to implement what we did on the whiteboard into Python. So before we start, we'll explain the libraries we'll be using today. So we'll be using NumPy for our arrays that we'll be using as vectors, and then we'll be using scipy.integrate for our solver pound and IVP. And just a quick note, a solver pound IVP is basically a solution solver, but for differential equations. So this is perfect what we need because we are using differential equations for our three drain tank system. So now first, let me put the initial values that we had that we know from the start of our equation. So we know the initial Qn is equal to 1 meters cubed, 1 meters cubed per second. We know that now the new flow in, which is equal to 0.75. Okay, we know the cross-sectional area of the top of the tank, which is equal to 1 meter squared. And we also know let me put the units here. And we also know the cross-sectional area of the whole of the discharged liquid. Okay, so that would be AH, now equal to 0.05. Okay. And then that'll be squared. And the last thing we know is the initial height for all three tanks. And remember, we use that as a formula, saying that 1 over 2 times gravity times times Qn divided by cross-section area squared is equal to height. So let's plot that down. So H naught is equal to parentheses Qn minus divided by AC and then squared divided by times. Oh no, divided by 2 times gravity. Okay. All right. Should enter. And we're all set to go. So now the code is pretty simple for this word plot problem. So we first know that we're trying to find our right-hand side of our equation for the change of height with respect to t's. So remember, dh over dt is equal to qn minus q out, which we have an equation of q out as well, which we'll depict later in the code, and then divided by the cross-sectional area. So we know we're trying to find our right-hand side, which is what I just said. So define RAS of retake system. Oh, I think I already did that. Thanks. And then we are using respect to time and volume. Okay. Now, one thing we can say for our volume is that we know all the heights, initial heights, have the same exact value. So we know for height 1, height 2 for the tank, for tank 2, and then for tank 3, they're all equal to V. All right, so I go to the same volume starting off, and that'll be put off in our return slot when we get there. Okay, so now let's list off our leaving flows of our 3 tanks. So let's start with Q1, which we know is equal to AC, cross-sectional area, of times square root, so MP square root of 2 times gravity times height of the first tank. Okay. So then this would be the same formula for all 3 tanks. So for Q2, this is equal to, well, let me make this space. This is equal to copy and paste. And this is change the height to H2 and the same thing for Q3. Okay. Copy paste, and this should be 3. All right. Then for our return, we will have, now we have to plot this as a list now. So they can be input as a list in our answer. So the list for this would be like our assumption, we just plotted Q out for what we got here. So now we need to plot in Q in. So this would be first one for tank 1, Q in minus Q1 divided by H, divided by AH. And then we have the next. Okay. So we have Q1 minus Q2 divided by AC. Actually, this is AC. My apology. This is AC. This is AH. Okay. This is AH. Because it's a modification of the aircraft section area of the whole leaving, not the whole of the top. So these outlets is AH times square root of 2 times 3 times the height of the initial of the tank. In the formula for the change in volume is Q in minus Q out divided by the cross-sectional area of the inlet streams. All right, so now this is correct. Then for the next one, we will have Q2 minus Q3, and then divided by AC. All right, and return enter. Insert enter. All right, and then the last thing we need to do is use our solver function for this differential equation. So we'll do solve found IVP. And then for this, I'll pull up the web page for this. We need to have a function, a time span of how long this solution will go for, an initial guess or initial height of our reaction. So this would be our initial heights. And then since we're doing a continuous reaction, so this output is the whether to compute the continuous solution, and it automatically defaults as false, so it means it's not going to be a continuous solution. But for this stream, this will be a continuous solution. So we have to say this as true. So we're using these 4 steps in a solve IVP function. Okay, so let's start with our function first. So, all right, so our function is the right-hand side. So RES, we just copy paste this right here. So 3 tanks. Thanks. Okay. Next is RT span. And for here, I also want to add 10. So this 10 represent the time function of the solution, the solver will stop running. So we can put in 10,000. Make sure it runs everything correct. It needs to be in seconds. Okay. So we'll have, let's see, 0 to 10. Let me make sure this is correct. Okay. 0 to 10. Next, we need to have our initial heights, which is to be also in the list since, our differential equations, our change of volumes are on list. We need to have the initial heights in list as well to use this solver function. So this would be H, it's not. So this is for tank one, tank two, and tank three. Okay. And lastly, the dense output. So dense output. So dense, right? Yes, output. And this would be equal to true. All right. So enter. All right, and here's what we get right here, but we want to see the actual in an array. So let's make this into as a variable. So we say result. So we'll put res is equal to this function, shift enter. And then, so we want to see this fully plotted out. We do res dot solve. And then we put the time variable in this. So we can say for 5,000 seconds. Okay. And as you see here, we see there's three tanks and the heights of the three tanks after 5,000 seconds. And as you see here, the three tanks are very close to being fully even out at this time. If we want to change it to see what it looks early stage, we do 50 seconds. Oh, shift enter. And as you can see, oh, let me change the 10. This is 50,000. Shift enter. Okay, this is weird. Let me just go back to 500. 5,000. Okay. This is kind of this is kind of weird, but as you see though, 10,000. We do this 1,000. But as you see, you can see the change, so you can see the difference in the tanks as they go. This. Oh, actually, I do peep my mistakes. This needs to be an array. So the MP dot array. I was wondering why you didn't see the full change. So shift enter, MP dot array. Okay. Now let me try this. Initial heights, queuing AC, vision, vision. Okay, well, I don't know the full problem for this, but we do know that you can see here, you can see the change in height from our graph. I would like to see you have a full more example of this, but yeah, I don't know. Well, but you got to see it. This is the code. There's a small error, but we can get it changed later. I may update this, but yeah, that's basically it. You see the change in the height, depending on where the volume of the flow of the tank is. I mean, the flow of the liquid in the derivative time, change of time for the tanks. And yeah, that's the code. You know, yeah. Okay then. Nice. Well, this video helped you guys out, and see you guys later. Bye. Hey guys, I just want to fix up the little mistake from the second video I made for the code for part A. So as we saw when we put in our solution IV in res and put the res out in a certain time interval, and we want to see the change of actual how the tanks move the different times duration. We had a little bit of problems yesterday. And today I will explain why this happened and what we can do to fix it so you guys on your side and my side can see the actual change. So I actually dug up into it, and then I found out that our initial heights was actually incorrect. So as you see here, it's actually plotted at 0.05, which is extremely low, and that's not where our tank should be at. And it stems from this bad boy right here. So we actually have the cross-sectional area at the top of the tank instead of the whole of the tank, which we acknowledged in our equation on whiteboard, which should be AH. Okay, and also what we forgot to do is we forgot to put our gravity. I forgot to identify what our gravity is in our system, which is 9.8. Well, G is equal to 9.8. 9.8. Oh my gosh. 9.81. Alright. So once we did that, okay, now we should be good. So we control shift enter, and then we update our height here, and now we get 20 meters for our height, furniture height. So now when we run this now, this should be the correct values. So when we set our res, we get this. Let's put this as 50. Okay. So let's see what happens into 50 seconds. Okay, and then you see now you see actual change. So tank one would decrease more. Tank two is in the middle, and tank three it doesn't really see the effects of the lower inflow of the 0.75. So now this is what an actual accurate depiction of what the tanks were like. So we did only went 5 seconds since the tanks the flow decrease. You see that you only see the one change in tank one, tank two, and tank three really hasn't been affected that much. And then if we say it's been 500 seconds, you see the tanks finally start to level out. So yeah, so now this is what it should been. That's what the code should have been out like. Hopefully this helped you guys. Definitely helped me out. And that if you copy this down and walk through this like I did, you now can see the correct code. Was this how it is supposed to be like? Hope this helps and see you guys later.